In this session, we're going to look at translating and reflecting, and we are talking about graphs of functions. And to see what's going on here, I want to start with something that you should remember, and that is the graph of a parabola. The function, of course, being f of x is equal to x squared. And what we're going to do is we're going to use what we know about this graph to draw a new graph. That graph being f of x equals x squared plus 2. In other words, we're going to find out what happens when we start changing the function around a little bit. Well, I need some axes. I think I'd like to look at this from the perspective of an XY table at first. Generally speaking, though, what I tell folks a lot is if you know a shape and you know where to put it, then you can draw a graph. And you'll see what I mean as we go. I'm going to pick values that we're familiar with here for inputs like 0, 1, 2, 3, see what happens with outputs. And of course, if we put these values into the function x squared plus 2, then 0 is going to give us 2 as an output, 1 will give us 3, 2 will give us 6, and 3 will give us 11, if I'm doing my math correctly. Plotting these points will give us a picture that, well, we have a dot here at 0, 2, and then at 1, 3. And of course, the parabola is symmetric with respect to the y-axis, so we have a dot to the left of the y-axis. 2 will map to 6, and then 3 will map to 11. And of course, we have those corresponding dots due to the symmetry of a parabola. And then cross my fingers. No, didn't like that. Remember we talked about the curve that a parabola has down there at the what we call the vertex. And I think that's about as good as I'm going to get right now. And what you can hopefully see is that it's the same shape as what we have in this other graph, the computer generated one. But each point has been moved up by 2 units. In other words, this is what happens when we add 2 to the previous y values. So f of x equals x squared plus 2 has the shape of the parabola, which we could glean from the fact that it's x squared, but all of the points have been moved up by 2 units, and that's the effect of the plus 2. That's what I mean when I say if we know this shape and we know where to put it, then we can draw a graph. Let's see how that works out in the next example. It looks like there's a lot here, but it's basically the same thing as what we just saw, except a reminder graph is f of x is equal to the absolute value of x, because what we're going to sketch is the graph of f of x is equal to the absolute value of x plus 2. Here for reference we have the shape of the absolute value graph, which is of course in the shape of a V. And if I want to use the XY table, I can. The absolute value of 0 is 0 plus 2 gives me 2. If I input a 1, I get a 3. If I input a 2, I get a 4, etc. Or I can recognize that the shape is the absolute value graph. The plus 2 is going to mean that the previous shape that we had is going to be moved up 2 units. And so what I can actually do is just draw the absolute value shape that I know, but it's been raised up 2 units. And this is what we call a translation. The original graph has been translated up 2 units due to adding 2 to what had previously been the output. Now let's see what happens when we mess around with what's inside the argument. Here we have directions to sketch the graph of each function. The functions are f of x is equal to x plus 2, the quantity squared, and f of x is equal to the absolute value of the quantity of x plus 2. The shapes are going to be the same shapes that we saw before. And what indicates that to me is the squared portion and the absolute value bars. Okay, So that indicates to me what we refer to as a parent function, or as a student said one day, a mother function. I'm again going to explore this from the perspective of an XY table, and I want to start with a value that's going to make the inside of the parentheses for f of x equals x plus 2 the quantity squared. I want to start with a value that's going to make inside the parentheses equal to 0. That's going to be the number -2. And of course that output is going to be 0, because when I square 0 I get 0. And that gives me a point on the x-axis, -2, 0. Now I want to pick numbers to the left and the right of that, so maybe -3 and -1 and 0. See what happens with outputs there. F of -3 is going to give me -1 squared, which is 1. F of -1 squared is going to give me 1 squared, which is also 1. And then f of 0 is going to give me 2 squared, which is 4. And so let me go ahead and plot those dots, plot those points. And what I'm seeing is the same basic shape that we had before, a parabola, but it's actually, in this case, been moved to the left by 2 units. That's what the effect is going to be of something that's inside the argument. It's a what we call a horizontal translation. In the next graph, f of x equals absolute value of x plus 2, it's again going to be a translation in the same direction, and for basically the same reason. What zeroes out the argument? Well, that's if x is equal to -2. So a dot here, a point at -2, 0. And then I'm just going to draw the shape of the absolute value graph, which is basically a V. And that's good enough. That's kind of what we mean when we say sketch. I do want you to give it, you know, the old college try. Make it look pretty, but it's not a requirement that it has to be perfect. But basically what you're showing me is that you know the shape and you know where to put it. So let's see how this looks in the next example. We're asked to sketch a few graphs, and we'll just do each one in turn. The first one is f of x equals x cubed plus 1. Now the x cubed is indicating to me the parent function. And so I recall the shape of a cubic function from a previous video. If we've been paying attention, then we'll know that the plus 1 indicates that the graph is going to be moved up by 1 unit. And so I'm going to draw the shape of the cubic function that I know, but instead of starting at the origin, I'm going to start 1 unit up. And then as I recall, the cubic function goes high in the first quadrant, wiggles in the middle, and then goes down into the third quadrant. And it's the shape that I know that's been moved up by 1 unit. See if you can use what you just saw and what you know to sketch the graph of f of x is equal to x minus 3, the quantity cubed. Okay, so cubed tells me the parent function, the shape, and then x minus 3, well, let's go back to the previous slide. When the argument was x plus 2, I moved to the left by 2 units. So here the argument is x minus 3. If I think about what would make inside the argument equal to 0, then that might help me to see that I'm going to move to the right by 3 units. And it's the same shape that we had before. Move to the right by 3 units. Now I know this isn't perfect, but I think it's pretty good. Let's combine these two ideas, that of moving a graph up by 1 unit and to the right by 3 units, for our next example. Sketch the graph of f of x equals x minus 3 the quantity cubed plus 1. So the way I'm reading this is the quantity cubed portion indicates the shape that I'm going to be drawing. X minus 3, inside the parentheses, that's going to be a left-right translation. In fact, we call that a horizontal translation. And then the +1 outside the argument is what we call a vertical translation. So the way I'm thinking of this is knowing the parent function tells me what the shape is. And the general shape would be this cubic shape. But enter the translations. What I really suggest is that you find a handle for each graph and figure out where it goes. Let me back up a couple of slides and show you what I mean. For the parabola, I think of the handle as the vertex, and if I know where that vertex is going to go, then I can draw the graph. Likewise for the absolute value graph. If I know where the vertex is going to go, then I know I can draw that graph. This was also indicated in the previous horizontal translations. In the graphs that we just saw, I didn't tell you I was thinking of it this way, but the handle that I'm thinking of is where it wiggles most, the kind of the center of the graph. And so here I have in blue the parent function, and if I consider where that center part is going to go, then that helps to guide my drawing. Let me clear this up just a little bit and draw the shape that I know it is, but move to the right by 3 units and moved up by 1 unit. I know that that handle would go through the origin, and so if I move to the right by 3 units, that's going to be the point 30, and then up by 1 unit, it's the point 31. And then draw the shape that I know that this graph has, taking care to do a decent job with it, and that would pretty well be good enough for me. On to the next. Now we look at a different type of transformation. In this case, we're asked to sketch the graph of f of x is equal to negative x squared, and then follow it up with f of x is equal to the negative of the absolute value of x. If we consider xy tables and inputs of, say, -2, 0, and 2, for instance, then f of, let's make sure we don't let the order of operations get in our way. F of -2 is going to be the negative of -2 squared. The answer there is going to be -4. F of 0 is going to be 0. F of 2 is going to be the negative of 2 squared, and I'm only using parentheses to indicate that the negative in the function definition of negative x squared isn't being squared. The output there is again going to be -4. And as a matter of fact, with this negative out in front of x squared, that means that the answer is never going to be positive. This is actually going to give me the same shape that we saw a few minutes ago for a parabola, but it's going to be upside down. Wow, that's not behaving itself. Arrows there. And so that's basically going to be the effect of a negative out in front of the parent function. It flips the graph upside down. Likewise, for the f of x equals negative absolute value of x, it's going to flip the graph that I know, that v, upside down. Same shape, different orientation. These are called reflections. So that's what's meant by translations and reflections. That's the title of this episode. And now we'll see just how all these things can band together against us. Sketch the graph of f of x is equal to negative square root of x plus 5 minus 2. See if you can think of the parent function and apply the transformations that we've seen. Okay, the parent function is the square root function. As I recall, that has a shape of half of a parabola on its side. I see that the whole thing is reflected upside down, and is translated to the left by 5 units and is translated down by 2 units. Again, how do I know it's to the left 5 units? Because the argument is x plus 5, and I'm thinking of what would make inside the radical equal to 0. As far as down 2 units, anything that's outside of the parent function, the sign doesn't change, you see. It's basically subtracting 2, which has the effect of moving everything down 2. I talked about a handle, and it seems to me that for the square root function, the handle would be the point where it touches the origin. And so that point is going to move to the left by 5 units and then down by 2 units to be at the point -5, -2. And then we have this reflection that we talked about. And so the graph is going to be an upside down version of the square root function. And that's about as bad as it can get with these two ideas. Basically what you need is the parent function and then the different ways that it can be translated and or reflected. But we don't have to have one of our basic functions in order for this to happen if you know the shape. So in our next example, we are given a shape and we're asked to use its graph to sketch a transformation. So here I have the graph of f, and I'm asked to draw the graph of y equals f of x minus 2 plus 4. Well, we have a number inside of parentheses and we have a number outside. The one inside the argument is going to be a horizontal translation. We change the sign on what's inside the parentheses, essentially figuring out what number makes it equal to 0. And so that means we're going to shift to the right 2 units. We have a horizontal translation there. And then outside the parentheses we have a plus 4, and that's going to shift our graph up 4 units. In order to analyze how this is going to happen, what we're going to do is we're going to pick points that indicate defining characteristics and then figure out where those points go. But then ultimately you'll see how the transformations work together. So let me mark some points that seem to me to be corresponding to defining characteristics. And then let me label these points. And so the points that I've identified that seem to be of interest are -5, -5, -2, 4, about 1.5, 4. That's a squiggly, not a negative. 3, -4, and then 5, 5. Let's figure out where each of these points lands under this transformation. We'll start with -5, -5. According to what we've written down, our graph is going to move to the right by 2 units and then up by 4 units. The effect that's going to have is that we're going to add 2 to the x-coordinate, and then we're going to add 4 to the y-coordinate. So under this transformation, the point -5, -5 will move to -3, -1. Our next point of interest was -2, 4. So the point -2, 4, again, because of the transformation, is going to have 2 added to the x-coordinate, 4 added to the y-coordinate. That's going to land us at 0, 8. Now we could continue on with this process, but I'd like us to look at it in a slightly different way now. So I will go ahead and make use of the information that we had. -3, -1, we have a point there. And then 0, 8, we have a point there. And then let's see what how we can apply the transformation more kind of visually. It's going to have the effect of moving the point that would have been at about 1.5, 4 to the right 2 units and then up 4 units. I'm going to start to draw this because I'm going to get lost with all the dots right here. And then the point at the local minimum, 3, -4, is about here. And then we're going to move to the right 2 units and then up 4 units. And then finally the last, the endpoint, 5, 5, moves to the right 2 units and up 4 units. And so that swoops down to the local minimum, which is now on the x-axis, and then back up here to what looks like to be 7, 9. Finally, we have used the graph, same function f, to sketch the indicated transformation, but this time it's y equals negative f of x plus 3. Well, the negative is going to be a reflection, so the thing is going to be upside down. And then the f of x plus 3, that's going to shift to the left by 3 units. I'm again going to find out where defining characteristics points go. Negative 5, negative 5. The negative reflection means that's going to end up at negative 5, 5. But then to the left 3 units indicates that that's going to be, it's actually going to end up at negative 8, 5. The point, what was that? Negative 2, 4 is going to be flipped. So it would be at negative 2, negative 4, and then it's going to be moved to the left by 3 units. The point in at the end of that horizontal segment, 1.5, 4 is going to be 1.5, negative 4. And then again, move to the left by 3 units. Now I'm going to start to get confused if I don't start to draw this thing, so that's exactly what I'm going to do. Connect those dots, connect those dots. This point down here at the local minimum was 3, negative 4. And that point would land at 3, 4. So that flipping up and flipping down that we've been doing, that's because of the reflection. And then we take the result of that and move it to the left 3 units, and that's the result of the translation. Finally, we have the point 5, 5, and that's going to land first at 5, negative 5, and then move to the left by 3 units. And so here we have what will now become a local maximum, and this is what it looks like to flip or reflect and then translate the graph over 3 units.